floor of the lateral ventricle. So where would we find it, guys, would be like right over here. So here would be the roof, the corpus callosum would be sitting here, the fornix would be sitting somewhere down here. Now, in between the corpus callosum above and the fornix below is this little membrane right there. That is the septum pellucidum. If I took like a little pick and I poked through there, I would be right in the chamber here. So the septum pellucidum is kind of the wall, the side wall of the lateral ventricle, which is inside there. And so everything's kind of arranged around this ventricle system that's inside the cerebrum. Okay? Again, corpus callosum would be up over here. Right? The septum pellucidum would be here. Actually, the fornix, I take it back, would be over here. I went too low before. The fornix would be over here. And so these structures are all around there. Corpus callosum above, the fornix, and the septum pellucidum would be in here. I just took like a pick, and I went through this little area here. I would be in the lateral ventricle. Okay? So corpus callosum, septum pellucidum, fornix. Corpus callosum, septum pellucidum, fornix. And we're going to take out the anterior commissure. It happens to be missing on this one. Questions or comments? Okay. Again, corpus callosum is an important structure clinically because it gets our left brain to communicate with our right brain. Right? They need to communicate, so that's an important structure. So these are all neurons running across. Right? It's a whole bunch of tracks running across. Okay. Any questions on that? Finishes the cerebrum for me. It's main structures I need you to know. We're good? Okay.
So you're saying that the corpus callosum is all the neurons are the next.
The left brain? Yep. Exactly right. So if I separated this apart, the corpus callosum would be running. See how it's on both sides? So that this side communicates with that side when they're together. The signals are going that way. Corpus callosum. Okay. The next region of the brain, guys, is the diencephalon. Just to show you real quick. Is that one picture? I liked it. Okay, so just to give you bearings, corpus callosum, right? Septum pellucidum and the fornix. This area right below here, this is called the diencephalon. I could spend a week just on this region. It is so important. It does so many things. So we're going to make it nice and easy. Remember, anything that has the name thalamus belongs into the diencephalon. So watch this. See this thing here? It kind of looks like an almond. This is the thalamus. Okay. Then this region here, below the thalamus, is called the hypothalamus. What does hypo mean?
Below.
Below or underneath. So that would be that. And then on this one they don't have it, but above the thalamus is going to be the epithalamus. Let's get a picture of that. Yeah, they're not even really even showing it. They probably have it elsewhere. So what we're going to look for here, we're going to look for the thalamus. Again, it always looks like an almond. To me, it kind of reminds me of an almond. Then we'll look at the hypothalamus here, and then something called the epithalamus. Also notice on the almond, there's this little round circle. This is a crossbar so that the left thalamus can communicate with the right thalamus. So there's a little crossbar, so we're seeing part of that on section. So watch this. I'll go in here in the middle, and then I'll show you guys. Here was the fornix. So right about here, see that kind of almond-looking thing? You need no more taping? Run out of tape? You got to erase all your family. It's all got to go. So this is the almond. That is the thalamus. Thalamus. Okay. All that is the thalamus. Looks just like an almond. See this whole thing right there? Okay. Now watch this. I'll bring it back over here. This little bump on there, this is called the interthalamic adhesion. This is so the left thalamus can communicate with the right thalamus. So that little bump on the thalamus right there, it's kind of a darker brown, that is the interthalamic adhesion. That's this thing right here. Okay, so the whole thing is the Amon. You just, if I point to it next week, thalamus, interthalamic adhesion. It's just so that the left thalamus can communicate with the right thalamus. That easy. What's the thalamus do? So watch this, guys. This is an important function. All that sensory information coming up from your body that's ultimately going to end up here, let's say for sensory perception, or visual here, hearing here, smell and all that kind of stuff here. All that sensory information coming up, before it gets to the cerebrum, it stops at the thalamus. And the thalamus is a relay station. It sends the signals to the proper place. So that, let's just say visual signals, once they come from your eye, the signals go to the thalamus, and then the thalamus sends it to the occipital lobe. The hearing, once it comes from your ear, the signals go to the thalamus, and then the thalamus sends it to the temporal lobe. If I touch Joanne here on the shoulder, we want the signals to go to the shoulder area on the postcentral gyrus. All right, so think of the thalamus as sending the signals to the correct destination for perception. And here's my analogy. I think most of us have been on the Long Island Railroad sometime in your life. Let's pretend for a minute we want to go to Penn Station in Manhattan. So you have Huntington line, you got the Babylon line, the Main line, Long Beach has a line, and Hempstead, all these lines that could take you to Penn Station. What's the station that you stop at first before you go to Penn Station? Where do we always stop? Jamaica train station, right? At Jamaica they say track 1 for Penn Station, track 2 for Woodside, track 3 for Brooklyn, that type of thing. So Jamaica train station is a relay station. It sends you so that you go to your proper destination. That is the thalamus. If you didn't have the thalamus, you know, what's going to keep eye signals from going to your occiput? It may go to your temporal lobe, right? You would be able to, you'd be going to the wrong destination. So the thalamus is like the Jamaica train station. It sends you to the proper location, okay? It's a really important function. All right, so the Amon is the thalamus. Hypothalamus. So now we're going to look over here. Kind of like this area here. This is the pituitary gland. You'll study this again next semester. So it's the pituitary gland sits right under the thalamus. This actually controls that. So next semester you'll talk about these two things again. So let's take a look at the hypothalamus while I get you guys here. Here was the thalamus. This area right here is the hypothalamus. Do I have mammillary body still on there?
Yes.
Cross that out too. Cross that out. So this is all the hypothalamus here. It's right below the thalamus.
Can I do it from I'm sorry.
Hypothalamus. Right, here was the thalamus, right below it, hypothalamus. Thalamus, hypo. Thalamus, and hypothalamus here. Thalamus, and then the hypothalamus here. So, this tissue to me is one of the most important pieces of the nervous system. It controls a lot of your endocrine system. Your glands, a lot of your glands won't do anything unless the hypothalamus tells them to. Next semester, you're going to learn 9 hormones that come from the pituitary gland. They don't get released from the pituitary unless the hypothalamus says we got to release them or not release them. Right? That's the director. It controls a lot of your nervous system. How about this? Anybody feel hungry or thirsty? Your hypothalamus is the one that sends out the hunger signals, the thirst signals. Even when you're full, let's say you've eaten a lot and you're full, that sense of fullness, that's from the hypothalamus. Body temperature, right? The fact that our body temperature always stays around 98.6, that is the hypothalamus that controls that. If your body starts to get hot, this is the one that turns on your sweat glands, vasodilates your blood vessels in your skin so that you lose heat. Right? This is doing all that, plus much more. Like I said, I could spend days just really teaching you the hypothalamus and all the stuff that it does. So it's an important piece of tissue called, again, the hypothalamus, right below the thalamus. Okay? Finally, guys, watch this. Above the thalamus, but below the fornix, is the epithalamus. So epi means above or upon, right? So for our purposes, on this model here, let's see what they have over here. I'll show you this one. It's kind of like this red and purplish area here. This is called the epithalamus region. It contains two important structures. What I'm pointing to right now is the choroid plexus. This is a network of leaky capillaries that are responsible for producing cerebrospinal fluid. So this is the choroid plexus right here. If you follow the choroid plexus all the way back, there's another gland. It's kind of like a red circular area. That's called the pineal gland. Have you ever heard of a hormone called melatonin? Sometimes you hear about melatonin. Melatonin is what makes you drowsy at night to fall asleep. It actually suppresses the nervous system. So here's the choroid plexus and the pineal gland. They are all part of the epithalamus. So they're located in the epithalamus, and those are the two parts, the choroid plexus and the pineal gland. Okay. Boom. The brainstem. Watch me for a second, and then I'm going to have you take off something also. Stay with me 1 minute. Just want to show you real quick here. Here we go. Watch this, guys. So this was a section of the sagittal section. Corpus callosum. What would this be? Septum. Pellucidum. Fornix. Right? Three structures go together. What's the Amon? Thalamus. The little bump on the thalamus. Interthalamic adhesion. Here's the hypothalamus. And then this area here would be the epithalamus right here, where the choroid plexus and the pineal gland are. So we kind of did all this already. The brainstem has three parts to it that I want you to know. This part here is I call it the midbrain. The reason I put mesencephalon there is your lab book calls it the mesencephalon. So just so you know, mesencephalon and midbrain are the same thing. This is the midbrain, the pons, and the medulla. So these three things are the brainstem, right? The midbrain, the pons, and the medulla, they form the brainstem. So do me a favor.
Can you show it again, please?
Yes, absolutely. So right below the diencephalon, the thalamus and the hypothalamus, this right here is the midbrain. The pons kind of reminds me of a walnut, right? This is the almond. This kind of has a walnut appearance to it. So midbrain, the pons, and then the medulla, and then the spinal cord will go from the medulla down, okay? Midbrain, pons, and medulla. So under the midbrain, cross out, only because our models don't show it all the way, cross out corpora quadrigemina, and then cross out the two colliculi underneath that, superior colliculus and the inferior colliculus. You can strike those. Just know where the midbrain is. So, well, once you're done, I'll show you here. So this was the hypothalamus. So right below it, this would be the midbrain here. The walnut is the pons, and then here is the medulla, and then this would be the spinal cord. All right, so midbrain, pons, medulla. Midbrain, the pons, and the medulla. The brainstem is responsible for a lot of very instinctual, primitive reflexes, things that you totally give no thought to. Things like your heart rate, the force of your muscle contraction, your breathing rate. Let's say you ate something toxic or poisonous, like a poisonous berry or something like that. Your brainstem is responsible for vomiting. If you breathe something in and it gets into your throat and you have that tickle and you got a cough, that is your brainstem that does that. So these are all very primitive, instinctual kind of reflexes. This is one of the reasons when people have trauma. Right there with a kid, they always tell you never hit somebody in the back of the head. You could kill them. Right? When you get hit in the back of the head here, all these centers that control heart rate and breathing could be damaged and it could be fatal. We actually had in my neighborhood, probably about 2 years ago now, a young guy, I felt so bad, he was in his early 30s, his kids were playing on the ground, he was working in the yard, he climbed up on a ladder and he went to cut a branch off of a tree with a small chainsaw. The branch came down in such a way, it knocked the ladder out from underneath him and he fell back like this. He was like 8 feet up or something like that. He landed on the back of his head. It was fatal because he landed right on the brainstem area right there. So it was, again, such an important area right over here. So very instinctual things, like I said, primitive reflexes, heart rate, breathing rate, force of heart contraction, vomiting, coughing, sneezing even, all happens over here, okay? So those are the things I want you to know for the brainstem. Okay, and that ends that model right there. The last two things. Any questions on those guys, where those structures were? Okay. The last couple things I want to take a look at are going to be the little brain, which is underneath the, let me put this back into perspective here. That ain't right. Just going to take it apart to do that. Okay. So the little brain is this, the darker one right here where my fingers are. This is the cerebellum. So when you look at the cerebellum, guys, just to show you too, watch this. When this is just the frontal section here. Notice this darker area here. This is the cerebral cortex. See how it's superficial? Right? Remember we said the cortex was superficial, and then here's all the white matter. So it's kind of a good representation of superficial cortex and the deeper white matter. Kind of a neat picture. What was I looking for? We're doing cerebellum, right? Where's cerebellum? I saw a picture before. Oh, here we go. So watch this, guys. If we were to take the cerebellum out, you're going to see there's like a butterfly, right? Here's the body of the butterfly, and then there's a wing and a wing. This would be the left hemisphere. This would be the right hemisphere. And so when you look at this, left and right cerebellar hemisphere. The body of the butterfly is this thing right here. This you're going to call the vermis. Okay? So you have the two cerebellar hemispheres. In the center is the vermis. That's this thing right here. If we cut the cerebellum, you're going to see this. You're going to see white matter that's going to look like the branches of a tree. So all this white matter is the branches of a tree. Then on the branches of the tree, this right here is all gray matter. So this is kind of like the leaves on the branches. So the cerebellar white matter looks like branches. It branches so much, they call it the arbor vitae. And I'll show you on this model, it's a little bit easier to see. So we cut the cerebellum and take a look. Kind of looks like shrubbery or tree branches. All that white branching in there, guys, that's the white matter of the cerebellum. That is the arbor vitae. Okay, so that's the white matter. Just outside the white matter, all the gray matter on the branches, that would be like the leaves. That would be the gray matter. Some people even call that the folia, which is like the foliage, like the leaves on the trees. So all that gray just outside the white, or even on the inside here, that is going to be the cerebellar gray matter. Okay, so the arbor vitae is the white. What does arbor vitae mean? The tree of life, believe it or not. So it kind of looks like the branching of the tree, and so they call it the tree of life. Okay, so those are the things I need you to know from me. The cerebellar hemispheres, the vermis, the arbor vitae, and the gray matter on the arbor vitae. Sometimes they call it the folia. It's just the gray matter. What's the cerebellum do for us? One is it coordinates your movement. Every movement you do is nice and smooth. It's not jerky. Like even to go to, if you sign your name, right? If you go to sign your name, you got your pen in your hand and you kind of go to sign, right? When you sign it, it's a nice, smooth, coordinated movement. Everything that you're doing all day long is smooth and coordinated. You can thank your cerebellum for that. It controls coordination. Okay. Your posture, the fact that you keep your head over your shoulders over your pelvis over your legs, right? Your cerebellum controls your posture. Muscle tone, right? Our muscles are always in a partial state of contraction. That's regulated by the cerebellum. Equilibrium, balance, all regulated by the cerebellum. You know who knows neurology really good? Cops. They know how the cerebellum functions. When you drink, or even drugs, but drinking more, it affects the cerebellum so that a cop knows that you lose your balance and your coordination. So they take you, right? They want you to walk on the line on the highway or whatever. A lot of people that are drunk can't do that motion, right? Especially with their eyes closed. Here's another thing, when the cops do this, not that it's ever happened to me, right? And they take their flashlight and they have you watch the flashlight. When the cerebellum is, again from inebriation, when you bring your eyes all the way over, the eyes will, when you're inebriated, will like flicker. That's called nystagmus. That is a definite sign of intoxication, and the handcuffs come right out. So the cops kind of know their neurology a little bit as far as cerebellar function, and it's a good way. And they relied on that a lot before. They had like the breathalyzer test. Now they all carry the breathalyzer, so they'll check it that way. That's an easy way. But what they're testing was the cerebellar function, because the cerebellum is affected by alcohol. Okay, so you should know the functions. Anybody questions or comments on that? Okay. The last thing is this. Let's take a look at the ventricular system. So the last model that you need to know for me, guys, is this one going to be right over here. Let's go back to that one picture. Oh, look at this. Here's the falx cerebri. These are all new pictures from your book. I have to look for these. Here's the tentorium cerebelli over here. Next semester, you're going to learn all these blood vessels that drain the brain. That's a good picture of the falx cerebri. Where is the ventricular system? Bear with me a moment, you guys. Sorry. This is the nasal cavity, right? The superior, middle, and inferior conch. You can see here's the cribriform plate. Remember the olfactory foramen in there? Here's the olfactory bulb. And this is how all the dendrites are hanging out. There's something like 50 million dendrites in each nasal cavity for smell. Can a dog smell better than us or worse than us? Better. A lot better, right? They have something like 300 million receptors in their nasal cavity, so that's why they can smell so much better. These are all new pictures. I've never seen these before. Here's that. Look at this. Eyeball. What nerve is that? Optic nerve. What's the crossing? Oh, I have all the answers there. Sorry about that. What's that crossing, right? That's an optic chiasm. Here's the olfactory nerve over here. I'm actually just looking for one picture. Hang on 1 second. Go back to the beginning. Oh, here we go. That's the picture. Slideshow. Okay, so watch this. Let's talk about how cerebrospinal fluid is made, and watch this. How does it get into the central canal? How does it get into the subarachnoid space over here? Because we said both of those structures contain cerebrospinal fluid. So watch this. In your left cerebral hemisphere, this big thing right here is the lateral ventricle. In your right cerebral hemisphere is another lateral ventricle. In the ventricles, cerebrospinal fluid is made. Right? So you're making your cerebrospinal fluid there. Guess what? You make a new batch every 3 hours. Right? We're together 3 hours this morning. So from the time you came here to the time that you leave, you've made a new batch of cerebrospinal fluid. So we're constantly making it. Now watch this. From the lateral ventricle, guys, the cerebrospinal fluid is going to go through a hole called the interventricular foramen. And now the cerebrospinal fluid enters another ventricle called the third ventricle. This is right by your diencephalon. Your thalamus is right on the side of this. This is a hole in the third ventricle for the interthalamic adhesion right here. So your third ventricle is a slit-like ventricle. Take a look over here. This is your third ventricle right there. See how it's like a thin slit-like ventricle? Lateral ventricle, so like 1, 2, that's your third ventricle. This piece coming down, right where my stick is, that is the interventricular foramen. This piece coming down right over here, into the third ventricle. So now the fluid's here. From the third ventricle, the fluid is going to enter this tube right here. This is called the cerebral aqueduct. And remember from the old Roman days, the aqueduct carried water, right? It was kind of like the plumbing system of the Roman Empire. So that's why they named it an aqueduct. It carries the water down to this triangular ventricle. This is the last ventricle known as the fourth ventricle. So from the third ventricle here, guys, this tube going down, that is the cerebral aqueduct. To finally, this triangular one here is the fourth ventricle. Notice it's in front of the cerebellum, but behind the brainstem. That's the fourth ventricle. From there are openings. One opening lets the fluid go down into the spinal cord. That's the central canal that I drew up on the board over there. But if you cut this on cross section, it would look like that. The other two openings let the fluid go into the, what space is this? Subarachnoid space, right? The subarachnoid space, because that's where the cerebrospinal fluid is. So from there, from the fourth ventricle, this has these openings, and I think I put it in the notes. They're called apertures. Right? There's one median aperture that goes into the central canal, and then two lateral apertures that go into the subarachnoid space. Okay? So this will be a station also. You guys tell me, what are these two structures? Lateral ventricles. Then the one midline slit-like structure, this is the third ventricle. Like this is number 1, 2, so that makes this one the third ventricle. What's the long tube going down? Cerebral aqueduct. To this triangular ventricle at the bottom is the fourth ventricle. Okay? And then the only other thing, again, between the lateral ventricles and the third ventricle, this is the interventricular foramen. We can see it from the front right there. And again, the hole right here where the third ventricle is, that's for the interthalamic adhesion. One thalamus would be over here, the other thalamus would be over here, but they communicate with one another, so that interthalamic adhesion goes through that little hole right there. And you don't have to know that for now, but I'm just saying, just kind of put it together. So you got about 20 minutes, guys. You want to take the rest of these pictures. Next week, before I forget, what time are we starting? We'll start at 9, right? Instead of 8, come at 9. I need a little bit of time to set up.
The septum, where's that?
So we had done that earlier. Watch this. Do I have it again on the notes? Yep. So watch this. Remember the corpus callosum and the fornix? This right here was the septum pellucidum. It was the side wall of the lateral ventricle. I think that's why I mentioned it again. On that chart at the bottom of page whatever, 3, you don't have to know that chart. That's the 12 cranial nerves. Again, there's not enough time. Just know how many cranial nerves? The first 2. Cranial nerve number 1 was olfactory nerve. You should know that in its parts, and you should know the optic nerve and the optic chiasm. The other cranial nerves you don't have to do. I won't ask you that.
That's fine.
Yeah, she's not going to get to it, and we could use another week to do that. So, all right, guys. So take the rest of the time. Make sure you get your pictures. Go over the models. Right about 20 minutes or so.